Hello, everybody. Welcome back to our training session. Today we have Priyam Mazumdar, who is going to give a tutorial on introduction to PyTorch. So we are very happy to have Priyam back. He delivered this tutorial and a couple of other tutorials in the last semester as well. And he is sort of a very passionate and engaged presenter for this, and so these tutorials are very, very popular and very powerful ways to get started with learning PyTorch. So Priyam, with that, please take over from here.
Yeah, it's nice to meet all of y'all. If you're having any troubles in like seeing anything, if the text isn't too big, just drop it in the chat and let me know, and I'll make it bigger. So the purpose of this tutorial is mainly targeted towards people who know some Python, probably seen like NumPy, Pandas, things like that, but really hasn't done a lot of deep learning or really any deep learning. There's obviously a couple of different platforms to do this. There's PyTorch, which I personally enjoy using. There's TensorFlow, there's some other new ones called like Dynet and JAX and all that. But I think PyTorch is kind of one of the most popular ones right now, mainly because it's very Pythonic in the way you use it. So we're basically going to be going over PyTorch, how it's very similar to NumPy, kind of the different abstractions that are available. And really, as long as you know like some NumPy, like the super basics of like what a Python class is and like a for loop, you should be able to do this without too much of an issue. And about 2 years ago, I learned PyTorch from this tutorial as well, and I've gone really far from it. So hopefully this gives you an idea of how kind of it all comes together. So let's just go over some prerequisite kind of ideas. So first, right, the functionality of PyTorch is very simple, similar to NumPy, in the sense that in NumPy, right, you're basically working with arrays of numbers. Well, in PyTorch, you're still just working with simple arrays of numbers. It could be 1D arrays, vectors, 2D arrays, matrices, or 3 or more arrays. So that's when you get into the tensor category. But there's two major, and there's many differences, but the two major differences between PyTorch and NumPy is that PyTorch 1 allows you to place tensors on the GPU, which allows you to accelerate compute, which we'll see in just a bit. And second, PyTorch, whenever you do any kind of operation on a tensor, it keeps track of it through its automatic differentiation engine. And so it allows you to do backpropagation, which we'll kind of talk about what that means if you haven't heard these terms before. So again, right, the prerequisites, if you just know the basics of classes, NumPy, and for loops, that should be sufficient to kind of get through this notebook. Everything in this notebook, also, you can do it on the HAL system. You should also easily be able to do it on Google Colab if you just turn on the GPU option. So if you want to follow along with me, that'd be a great place to do it. In the chat, I also dropped a link to the GitHub repository that has this specific notebook in it, and you can reference that now or later or whenever you want. So what are things you need to know for deep learning, right? Like to understand the theory of kind of how things are going on, all of deep learning essentially just runs on linear algebra. Honestly, you can't do much in machine learning in general without linear algebra. So having a good grasp of that is important to understand kind of what's going on underneath the hood. PyTorch obviously kind of abstracts a lot of these ideas away. Similarly, for kind of any kind of gradient-based methods that we use for the optimization of these deep learning algorithms, you need to know optimization and you need to know calculus. And then there's a ton of probability and statistics that kind of feed into it when it comes to like prediction steps and things like that. And we'll kind of see all of that soon. Things that are nice to know, right? And this is when you get into more higher level deep learning concepts, right? Understanding topology, kind of these high dimensional spaces. How do you kind of descend these complex spaces? Graph theory is really important in kind of two senses. First, how are the computational graphs set up for the deep learning algorithms to work to begin with? And two, there's a bunch of graph-based kind of prediction algorithms or deep learning algorithms that also exist. Next, knowing how to do partial differential equations, it's kind of based on the calculus, there is more depth that kind of goes into a lot of that. But honestly, really just as much knowledge you can get your hands on Honestly, I feel like everything I learn feeds into it one way or the other. So, just as much as you can learn is always great. So let's kind of get into the basics of what is a tensor and how is it, different. So like I said, if you have a one-dimensional array or list of numbers, that's just a vector. A two-dimensional list of numbers is a matrix. And these things everyone has worked with in some kind of math or computer science class. The complexity starts once you start adding additional channels or additional dimensions. So for example, a color image, right? Ignore the blue and green for now. Just think about the red, right? So red would just be a 4x4 image, right? So this would be a 4x4 matrix. But whenever we kind of describe our images, we often call them RGB images or red, green, blue color channels. And that basically says that there's this much energy in our red amount at this pixel. And then kind of the aggregation of our RGB at that pixel kind of determines the actual color that we visualize there. So this would end up being a 4x4 by 3 color channels. So you can see now we're at a 3-dimensional image, right? So this is why we need to use something called a tensor instead of just simple matrices. So we're going to create some tensors here, but first we need to go ahead and do all of our imports, right? So I'll kind of go through, if you haven't imported things in Python before, this is kind of how the notation works. So the most popular thing you'll always use as for kind of numerical processing will be NumPy. It's just your general matrix processing. Second, Pandas allows you to work with CSVs, comma set, basically data tables, things like that. So these two are definitely crucial. We're going to grab some stuff from scikit-learn just as a demonstration for later. Mainly, we're going to be doing a linear regression example. So we're going to do from sklearn.linear model. We want to import in linear regression, right? So this is our simple linear regression model from scikit-learn. Similarly, we need a dimensionality reduction model, and you'll see kind of what it is later. So my favorite one to use always is sklearn.manifold. We want to import in tsne. You don't really need to know how these things exactly work, but once we get to using them, I'll give you an intuition of what's going on. Next, these are all the things we need for PyTorch specifically. So we obviously need torch. We need torch.nn as nn, right? And torch.nn basically holds all the different modules that we need to work with the PyTorch layers, and this will all make sense soon enough. Next, we need to be able to optimize these functions that we set up. So import torch.optim as optim, right? So these gives us a kind of survey of these different optimizers we can leverage. There are a bunch of kind of tools that PyTorch offers in their functional, and this is where, let's see, should that be from sklearn.linear model instead of, you're right. Sorry about that. Thank you for that fix. I should just run things as I go. Okay, yeah, so this is import torch.nn.functional as f, right? And that gives us our, well, you'll see what they're used for in a second. Next, I generally like doing vision related things for the demo because it's easy to visualize them. So what we're going to do is from Torch Vision, we have a bunch of image transformations that we can kind of play with, and they're kind of stacked away in this package. Lastly, for plotting, we need, actually, let's put the plotter up here as well. So if you ever use it, matplotlib.pyplot is PLT, right? So matplotlib allows us to actually, plot loss functions or whatever you want to do. Lastly, for just some logging, so we can kind of see it train and see what's going on, we want to import in time just to keep track of like how long something might take. And lastly, we want to do from tqdm, import tqdm. TQDM is just something to make a progress bar. That's all it does. It just like in a for loop, it just prints out a progress bar of how long something takes. From Torch Vision, import transforms, not transformation. Whoops. Transform. Okay, cool. So those are all the things we're going to need. So let's just do some quick examples. I'm going to copy things in for some of it, and I'll type out other parts that's more tedious. So for now, let's just comment this out. Here is a quick example of a 1D data set, right? So essentially we have a list, right? And let's do it how we do it in NumPy normally, right? So if you do data right now, this is a list of 3 numbers. If you do the type of data, it's going to tell you that it is a Python object class list. Now, if you're used to NumPy, right, you do np.array, and now you have an array, right? This is your standard NumPy array that we use for any kind of numerical processing. Well, instead of doing np.array in PyTorch, we do torch.tensor. And torch.tensor wrapped around a list or a or a NumPy array, really whatever you want, and it will convert it. It'll convert it to this tensor type, and that's basically it. If we do a list of lists, so you can see we have a outer list, and then inside the list we have 2 more lists of 1, 2, 3, 4, 5, 6, right? This will basically, if we wrap this, and let's just actually do that. Cool. We can see again that we have a tensor, but now we have a 2-dimensional tensor. We have a 2 rows by 3 columns, right? So it's a 2 by 3 tensor, and that's it, right? This is how we can easily create tensors in PyTorch. Now, obviously, it's a little inconvenient to hand type out numbers, especially what if you need to generate, some kind of random tensor for whatever reason. So, NumPy has their random functions. Well, PyTorch also has its own random functions, and basically it's torch.randn. And in the parentheses, all you have to feed in is the shape of data you want. So if we do 3, that will generate 3 random tensors. So this is essentially a 1 by 3 vector. If we do a 1 by 3, obviously the numbers will change, but you can see it's still a 1 by 3. If we do a 2 by 3, now we've generated 2 rows by 3 columns. And then if we do a 2 by 2 by 3, we're going to have essentially this is our first channel of 6 numbers. So the first channel of 2 by 3, and then the second channel of 2 by 3. And these tensor shapes get much more complicated as you kind of increase the number of dimensions as expected. But it basically this is the idea of how we can just randomly generate some. Regardless, let's go ahead and take a look at AutoGrad, right? And this is really the meat and potatoes when it comes to PyTorch, right? This is what makes it really special. So basically, if you have a tensor, and if you set the attribute of this tensor to require grad as true, so by default, when I created a tensor, all these tensors up here, all these tensors up here, all these tensors that I've created, by default requires grad will always be set to false. So we need to essentially set it to true to kind of enable these computation graphs to be created. But when you do that, and whenever you do any kind of computation on that specific tensor, it tracks all the computations done on it, such that when you call dot backward, it will compute the gradient. And this will make sense in this very simple example. So if we have some function, f of x is 3 times x plus 2 whole squared, well, we can directly take the derivative, right? So the derivative of fx, or f prime x, would be 2 pops out in the front. So we have 6 times x plus 2 times the derivative of x plus 2 is just 1. So 6 times x plus 2 would be our thing. And this is our derivative with respect to x. So at the value of x equals 1, we'll have 6 times 1 plus 2, 3, so 18. So we expect our derivative value to be 18 at the value of 1. So we can actually do this in PyTorch pretty easily. So let's just create a quick tensor here, and let's do x is equal to torch.tensor, right? And the tensor is going to be on the value 1 or 1.0, so it's a floating point number. And then we need to just set requires grad equals true. So if we do this, we can check what x looks like. And you can see x is, the number 1. The number 1 is what we want to pass into our derivative function. And we can see that, requires grad is true. So, and that wasn't there in the previous ones. because by default it's turned off, so it wouldn't be there. So let's quickly just kind of do this computation that we see above on it. So first we're going to do y will be equal to x plus 2, and then some z, right, because it's essentially two nested functions, will be equal to y squared, and then it'll be that times 3, right? And if you look at z, not 2 equal, just 1. If we look at z, the value is 27. So let's actually, and so that's basically we plugged in 1 into here, right? You end up with 3 squared times 3 is 27. So let's just print out y, and print z, so you can see what it looks like. You can see that y was done through addition, right? And you can see that when we print out y, it kept track of the gradient function applied to it, right? So if we want to work backwards from x to y, from y to x, we need to take a derivative on the addition function. Similarly, when we do this computation to work backwards, we need to take the derivative on a multiplication function. If you can see, add and multiply. So you can see it's essentially keeping track of what operation was done on x, such that I can work my way back from z all the way to x. And this working back will just make sense in just a second. So then we can do z dot backward. And essentially what this backward is going to do is apply basically all the gradients, right? So up till now, we've only calculated, or all it's stored is, hey, I've added something. Hey, I've multiplied something. Basically what's happening here. But when we take the derivative, right, we need to keep track of, okay, so we added something and we multiplied something. So to take the derivative, we need to first deal with what's being multiplied and then chain rule it with what's being added. And so similarly, we deal with multiply and then add. This one's going to first apply the gradients because of multiplication times the gradients due to this addition. There is a little bit more nuance in that, but that's kind of at the high level what's going on. And then we can take a look at x dot grad, right? And we can see we get our 18 value, right? Which is what we expected f prime of 1 to be equal to. Does that make sense? Is there any questions? Yeah, so basically PyTorch is taking this gradient engine that I've just demonstrated and applies it in huge scales. And there's a lot of cool stuff that it does outside of this, but this is just the general idea of what's going on. So my favorite example to demonstrate kind of these deep learning concepts will always be simple linear regression, right? So for any of you who haven't seen this too much, basically simple linear regression is you have some x features. Let me zoom out just a little bit for this one. You have some x features, you have some y features, right? So this is a 2D input essentially, and you have all these points. And your goal is to fit a line to this point such that you're kind of tracking the general trend. Now, how does linear regression exactly work, right? What are we exactly doing here to be able to, what are we minimizing? What's happening? Well, here's the general idea. So first, linear regression can be written in this form, simple linear regression, where you have some W0, which is a bias term, plus W1 times X1. And so basically this is your y equals ax plus b, if most of you all have probably seen that form, but I'm just writing them as weights, so it's a little bit clearer, right? So we have some bias and we have some coefficient of x. And so to figure out what y is, you need to do whatever W0 and W1 end up being, it'll be W1 times x, plus the bias. And what are we optimizing? Well, this is what we're optimizing. This is called our mean squared error loss. And the reason it's called mean squared error is we're essentially looking for what was the true y, what was our predicted y, and the square difference between them. We do that for all our data, add it together, and then get the average. And so more specifically in the image, right, our error is if you take a point and just draw a vertical line, wherever it hits the red line, that distance between the blue dot and the red line would be our error, and we square that error. The reason we square it is so we penalize higher errors, right? Because 10 squared would go to 100, but 2 squared would just go to 4, right? So we're penalizing higher errors through this optimization schema. If you've taken any statistics courses, or like, I guess like EC 313 or something like that, you've probably actually seen this derivation of if you take this optimization procedure, rewrite it in the matrix form, and then take the derivative, you can actually directly compute your gradients, right? Or compute your weight matrix right here, right? So if you have some data set X, you can just do X transpose X whole inverse times X transpose Y, and you're good to go, right? There you go. You have your, you'll be able to directly calculate what W0 and W1 are, and you're done, right? So you basically have your equation that relates what's the relation between X and Y. There is a problem with this method though, the main one being numerical issues, right? So if we only have maybe 10,000, 100,000, whatever data points for X, so if X had 100,000, samples essentially, well, maybe we'd be able to invert a matrix of 100,000 by 100,000, though that is pretty computationally expensive. More specifically, if we have tens of millions of samples, inverting a matrix that large probably is impossible. So we have to essentially solve it via some kind of gradient descent method. And the deep learning model that we're going to be doing to do it essentially approximates it. It's along the same idea. But let's first try it with scikit-learn, generate some random data, and see what it looks like. So np.arange essentially will let us just generate a bunch of numbers between 0 and 10 with a spacing of 0.5. So we can see X is, here's our X value. Now, epsilon, we'll get to that in just a bit. Let's do Y equals 2 plus 3 times X. So what I've done here is I'm basically defining the model, right? So I'm saying the relationship between Y and X is 3 times X plus 2 will give me my Y, meaning that my Y values look kind of like this. And then if we do a simple plt.scatter, right? So this is going to allow me to plot a scatter plot between X and Y. Let's just make these sides of the dots a little bit bigger for you all to see. plt.show. Right, here's my data set, right? This is the data set I want to fit to. Now, again, I already know the slope of the line that's going to fit this is 3, and I already know the bias, right, or the intercept is 2 when X is 0. So there's like nothing fancy going on here, but this is, again, just for demonstration purposes so you can see exactly what's going on. So let's just quickly fit a scikit-learn model to it, right? So if we look at x.shape, we can see that we have 20 features as expected. I generally don't like working with arrays that have 20 comma like nothing. That's not a good way. I think it's good to define that it should be 21, 20 comma 1. So we're just going to do a quick fix on that. So X and Y will be equal to X dot reshape. And we want to reshape it as -1, 1 and Y dot reshape -1, 1. If you guys haven't seen the minus notation before, essentially it's saying that ignore what's happening here for now. We want to make sure that the last dimension is 1, right? So basically we want to put a 1 here, and whatever is left should be flattened and put in the front. In our case, we only have 1 dimension extra, right? 20. So we'll just end up with 20 comma 1. So here's our X. You can see it's like, like vertical now. But more importantly, X.shape is, 21. Okay, cool. So let's just create a quick model, linear regression, right? We're going to create a quick linear regression model. We want to do the standard model.fit procedure that they offer. And then what we want to print out is our coefficient and intercept, right? So remember, again, all the linear regression model is optimizing is what is the best W0 and W1 that I can pick such that I'm minimizing this mean squared error, right? So we can only optimize on these two. In this case, we can actually print out what they are. So we can do model.coefficient, right? Will give me my coefficient, and then print model.intercept and that will give me my intercept. Intercept. Yeah. And so, as expected, my coefficient should be 3 and the intercept should be 2 because I directly set the coefficient to be 3, intercept is 2. There's like nothing fancy happening here. Is there any questions? Does it make sense so far? Okay, I'm gonna assume we're okay. But again, just I have the chat open, so you can drop any question you have in there. But how do we do this with PyTorch, right? So scikit-learn probably took a look at this, saw that the data is pretty small, and just used our direct closed form solution to solve it. How do we solve this through initialization? Well, PyTorch, let's go through the couple of things before we actually do it. So the PyTorch class, you need to basically define at least 3 things. There's probably going to be more stuff that you can add as well, and you'll see an example of that too. But you need to initialize your class just like most other classes. You need to initialize the inherited class. So the torch.nn that we pulled in, this one here, we need to actually initialize it when pulling into the class. You'll see exactly why in just a second. And then a forward, right? So we're going to be setting up all these parameters and things for the model, but how do we actually pass our data through it? And so these are the 3 things that we have to do. If you haven't heard of gradient descent, the idea is very simple, right? If you have some cost function, right? So this could be our cost function of linear regression, for example. And given your 2 weights, W0, W1, in this case, it's just W. So actually, yeah, let's just think about it in this one. So if you have some cost, JW, up here, that means you have a high error or a high cost. And down here, you have a low error or a low cost. And your goal is to find for which W along these W axis do I pick such that I minimize my W. So the easiest way to do this is obviously W has to start somewhere by random. If you're very lucky, you'd start right at the middle, but in like every case, I've never seen it happen before, you never start right where you need to be, right? So you could start right here where this, for some W value here, you'd kind of start here. What you then do is you calculate the derivative of this function at that point that you're currently at, and you say that, hey, so if my derivative is this, I can work downslope or downhill by working down my derivative. Similar if you're on the other side, right, your derivative would look something like this, and you would just work down your derivative. And essentially, you're just going to take some steps, and you're going to do this procedure over and over again until you reach some minimum. Now, how big of a step do you take? We're going to be taking a look at learning rate a little bit later. But generally, the intuition is if you take too big of a step, your training would be unstable. But if you take too small of steps, then it'll just take you too long to converge. So you need to find like a an optimal step size to take for every iteration. But this is our general optimization gradient descent. There's a bunch of layers added to this, right? Because obviously our cost function's never going to look so nice and neat. They're very complex n-dimensional planes, and we have to include other concepts such as momentum and these other things, which you'll see in a bit. But this is kind of the bare bones idea that we have some kind of valley essentially, and we're trying to get to the bottom of the valley, and we do this by starting somewhere, calculating the direction that would lead us to that bottom, and then take a little step in that direction, and then rinse and repeat and do it over and over again until we reach the bottom. And that's basically it. So let's go ahead and build this model. So every PyTorch model, again, has a couple of things that you have to do regardless. So first, we're going to call this the stochastic gradient descent regression, right? That's going to be the name of this model. And the module we want to inherit, right, is our nn.module. So nn.module, basically everything you use in PyTorch. So you'll see linear layers today, convolution layers, but even more complicated things like transpose convolutions, transformers, all these other things, they're all stuck or defined in this nn.module. So we need to grab them from there. So first, we need to always have an init, and we're going to pass that for now. And then we always need to have a forward, and we're going to pass that for now. And I'll explain why the X is in here a little bit later as well. So all we need to do first is to actually initialize this parent model. So we can module. So we can do that with super, which refers to nn.module.init, right? And this would basically initialize that parent module that we're looking at. Next, what is this model, right? So we know that a simple linear regression has one input x, one output y, and that's it, right? Just one input x, one output y. And as for my definition of x and y, I defined x to just be a single value and y to be a single output, right? So we have one input of one value and one input of, or one output of one value. X could also have like many inputs, right? There could be 10 inputs to x and you could have 5 outputs to y. You can really have anything you want, but in this very simple example, we just have one input, one output. So that means we're going to call this layer I like calling him in this way. The fully connected one will be nn.linear, right? And we have one input and one output, and that's it, right? So this is the number of input nodes and the number of output nodes, right? And the word nodes will make a little bit more sense later, but maybe we can go through it. So we'll go over this again in a bit, right? But this is your standard linear. This is what I mean by linear neural network setup. So a linear neural network means that you have some inputs. These here are called hidden states. So we'll talk about those in a bit. And then you have some outputs. And essentially, you have these weight vectors. All these connections between them are called weights. And then each node also has an individual bias, right? So if we just take a very simple example of our model would essentially be, maybe a little bit too big. If you take one input and one output, that's it. Everything else is basically not our model right now. So if you just took these two, you'd have one input, one output, a single weight, and a single bias that kind of pulls it all together. So, and we'll kind of go through all this again. But either way, we have FC1 and nn.linear. And now all we need to do is in our forward function, we have some input value x, which again just has a shape of 1 because there's only one value. We need to know how do we pass it through this module that we just created. Well, so y is going to be equal to self.fc1, and we're just going to pass in x, and we want to return y. And that's it. This is our very simple linear regression model. Is there any questions to this? Okay, yeah, so yeah, again, the only 3 things we need to define the init. Inside the init, we have to initialize the parent class. Inside the init, we also, you don't have to do this inside the init, but it's recommended at least. Inside the init, you should define the layer or layers that you want in your model. And then in the forward, how do you take some input data and pass it through your model? And that's basically it. So now our model will be equal to this SGD regression that we just built. Now, what are the things we need for a deep learning model? Well, we obviously need the model first. Next, the loss function, right? So what loss do we want to minimize? In the regression case, mean squared error or L2 loss is kind of the most typical, though there are other ones for different reasons, but our loss function will just be torch.nn.msc loss. You can also write your own custom loss functions if you needed it for some specific case, but we don't. We're just going to use the standard mean squared error loss given by PyTorch. Lastly, the optimizer, right? How are we going to optimize this? Again, there's a ton of different optimizers. We're going to use the simplest one called stochastic gradient descent, which is based on this principle that I explained here. So we're going to do torch.optim.sgd, right? So our stochastic gradient descent. Now into the optimizer, we have to give it 2 things. First, what are the things we want to actually optimize? What are the parameters we want to optimize on? So just to give you a quick idea, if we look at our model, right, we can see our model has one input feature, one output feature. If we do model.parameters, we can see we have a generator, so we can do for param in model.parameters. We can print param, and we can see that we have these two parameters, right? Now it's kind of hard to tell what exactly these parameters are. So we can do model for name param and model.named parameters. And then we can print the name, and then the parameters. So in my fully connected one, right, FC1, the name is, first one is a weight, right? So this is essentially my coefficient, right, of my, or W1 in this case, right? So this was my W1, the coefficient, the weight. And then the second one is my bias. So this is my bias. You can actually also do like bias equals false right here. And so that would turn the second one off. But if you think about it, like logically, if you tried to fit a regression model without a bias and you could only control the slope, well, you just be pivoting around the zero. You'd just be pivoting around the origin, or pivoting in a line that goes through the origin. To Ron, where can we find the lectures to recordings to these lectures? Yeah, they will be recorded. I can't remember exactly where. In the NCSA, if you like type up NCSA HAL Training, you'll see the recordings in there, basically. It should show up. If it doesn't, just send any of us an email from the thing and we'll point you to it. Regardless, so we have our model, we have our loss, we have our optimizer. These are all the things we need. What are the things we want to optimize? We want to optimize this model.parameters, right? These are the things we want to optimize. Lastly, the step size, right? How big of a step do we want to take with every iteration? I'm going to do 0.01 here, but you have to kind of play with it and figure out what works best. Next, epochs. In epochs are basically how many times do we pass our data through the model, right? So we'll kind of talk about overfitting and underfitting a little bit later. But essentially, unlike some other models that essentially look at all the data and kind of optimize based on that, a deep learning model often needs multiple passes or looks at the data to be able to best generalize it. So we're just going to let this data pass in through 5,000 times and see what happens, essentially. So now we need to set up our training data. So X train will be equal to torch.tensor, right? It's going to be on X, and D type equals torch.float 32. And then Y train is equal to torch.tensor, Y D type equals torch.float 32. And this should be a Y, not a T. Right, so this is us, setting up our data. We take a look at X train again, right? Very simple. This is our very simple data set of that. Now let's take a quick look again at the thing that I had already pointed out. Right, so currently in this these weight parameters that you see right here, 0.7 and minus 0.6, they were just randomly initialized, right, by PyTorch. There is some rules to how they are randomly initialized, but as far as we're concerned right now is they're just randomly initialized. What we're hoping is by the end of training, this number should be what was it? It was 2x plus, or 2 plus 3x. So this should be 3, and this should be 2. That's what we're hoping by the end of training is what happens. So let's just see what happens. For epoch in range, if you don't know what the range function is, if you haven't seen that, print epoch. Basically, the range function lets us iterate from 0 to 4999, essentially, right? So it's just a iterator for us to kind of do something. What we want to do is our prediction, our Y pred is equal to model X train. And so model X train will automatically access the forward function and pass in our training data. You could also do model dot, no, let's do that. forward, right? You can also do model.forward_xtrain. They mean the same thing. If you want to do forward, this by default will access the forward function. So we have model xtrain. Our loss, right, is equal to the loss function. And this is the loss function, again, mean squared error from up here. And what is the loss between? The loss would be between our y pred, the prediction, and our ground truth data, so y train. Right, so this would be the loss. How far off are we, basically, is the question. Next, there's a couple things we need to do. So first, the optimizer, we need to zero out the gradient. So the optimizer, again, right, it's going to look at the loss, and then it's going to calculate gradients based on how far off was I in this prediction, right? So it's going to look at y, it's going to look at the true y, and then say, oh, I was off by like 200. So I need to now update my weights in this direction to actually, change the weights towards a direction where we'd be closer to ground truth, right? That's the whole purpose of this optimization procedure. The only thing is that when you calculate the gradients and then do it again, they accumulate, right? And now in some cases, like recurrent neural networks, which you'd learn in like later, gradient accumulation is an important thing to be able to do. In our case, we don't want to accumulate gradients. We want to calculate fresh gradients every time we pass data through. So before we calculate our gradients again, we want to make sure that we zero them out and just start from scratch, essentially. Then we're going to do loss.backward, right? And loss.backward is going to take, we're 200 off. So let's calculate the gradients to figure out how much do I need to change W by? How much should I shift our bias by, right? So that's all loss.backward does. And again, this is the exact same backward that we saw at the very start when we were doing the example, right? When we did z.backward, where essentially we've done all this math and now we need to calculate gradients. So let's calculate z.backward. And if we grab the gradient, right, we got that value. So very similarly, we just want to do optimizer.zeroGrad, loss.backward, and then optimizer.step. These three lines here is basically, you need it always, right? You can't really, except in some like specific scenarios, this is pretty general. You're gonna need to use this all the time. So, just, you can use it. Optimizer.step essentially says, okay, I've calculated the gradients. That's all good to go. I can see how far off my weight and bias terms are in this cost curve, right? So backward is going to calculate this black line here. It's going to calculate our gradient and say, like I need to move in this direction. And then optimizer.step will multiply the gradient by that learning rate or step size and take a little step in the what it thinks is the right direction. And so that's essentially what's happening here, right? So zero out the gradients, calculate the gradient again for the new data based on the new loss, and then take a little step in that direction. And it's just going to do this over and over again. So let's just do a if epoch mod, I don't know, there's 5,000 of them, so we can do like 500, I guess, equals 0 or equal 0. I just want to print out the loss.item. So we're just doing .item because the loss has like, well, it doesn't matter. The loss has like more stuff in it, like, information with the gradients and all that. We just need the, we just want the actual loss value. Okay, good. So let's give this a try. Let's see what happens. Great. So you can see in the very first iteration, right at the beginning, our error of our model and the true data, basically what the model compared, true data was 227. That's a massive error, right? Which makes sense, right? We're just randomly initializing the model. So of course there's going to be a high amount of error. But you can see slowly but surely, right? The error is essentially 0 at this point, which makes sense again, because we picked like a perfect line essentially. So there shouldn't be any error, but this is the error that we're dealing with. And if we take a look at this one more time, right? If you look at our models, 3 and 2, just like we set them. So this is how we can leverage gradient descent to solve this problem. And so now if you have a massive data set with millions and millions of samples, well, you can just use simple gradient descent to kind of pull it off. Okay, great. So that's all I have for that. Now we're going to go on to MNIST, right? So I'm going to copy paste some of this because it's more of a pain to type out and it really isn't about PyTorch much, but PyTorch offers some data set. This is going to break, isn't it? Because I haven't imported Torch Vision. So let's just import Torch Vision. There we go. Okay, good. Okay, so yeah, Torch Vision gives us, we have these data sets from Torch Vision. The MNIST data set is the one we're interested in. This is just save it in the root directory. In this one, I want the training data. If it doesn't exist, download it. And then there's this step in here called transform. And so these transforms are specific to the data you're working with. So torchvision.transforms offers a plethora of all, and we'll see some of them. We won't really use them because we don't need them, but they offer all these different transforms. The only one we're going to use is take the MNIST data, which is saved in I think a PNG kind of format in the data set itself. Just grab that PNG and convert it to a tensor. That's it. Just convert it to tensors, and then we can work with them. And this is essentially that torch.tensor function that we were using. It's just doing it inside our data set rather than us having to do it after the fact for simplicity. If you've never seen the MNIST data set, it's a very simple one, right? So I'm just going to print out a couple of this. So what we're doing is essentially this train that we see, when you iterate through it, it returns two things, right? The image and the label, right? So what is the image and what is the label? In our case, right, the image is this looks like the number 5, so our label is 5. This one, the image is like the number 0, so our label is 0, and et cetera, et cetera. 9, label is 9. So this image, label, and train, that's what this is doing. Again, I don't think I mentioned this already, but this method that we're doing of we have some input data and we have some label we're trying to map that input data to, this is called supervised learning, right? It's supervised because the training is supervised by some kind of labels. We're going to take a look at unsupervised as well a little bit later, but this is supervised learning. So for image, label, and train. The other thing to keep in mind is that image, label, and train is returning just a single image and a single label at a time. Similarly, in the linear regression example, we were passing in all the data at once, right? So when you pass in all the data at once, because there's only a little bit of data, that's called gradient descent. We cannot do gradient descent for basically every real world scenario, because if you have millions and millions of samples, you cannot pass in millions of samples into the network at the same time. That's just not possible. So instead of passing all the samples in at once, what we're just going to do is grab a random sample of these samples and just pass those in and just do that over and over again. So a single epoch will still be the entire data set, but instead of passing in the entire data set in one go, you're just going to grab 64 images at a time and pass them in, and then kind of calculate from there. And you'll see an example in just a bit. But let's talk about some neural, here, let me drink some water. Let's talk about some considerations when it comes to neural networks. First, the first one's batch size, which is what I was just talking about, right? So how many samples do we want to feed through the network at every step? What's the batch size you want to use? Well, there's a lot of research that shows that batch size of 32 or 64 is optimal. But we regularly do batch sizes of 1024. It's good to keep batch sizes to the power of 2 because there is some optimization that's done under the hood by NVIDIA and PyTorch and all of that to deal with powers of 2 batch sizes. Really, the batch size you use is limited by how much memory you have on your GPU or CPU in your machine to pass through at once. And you'll see if your batch size is, again, too large, you won't be able to fit it in your hardware. And if it's too small, the model's not going to see a wide enough range of data every time, and it won't be able to generalize. And there are some workarounds, but gradient accumulations out of the scope right now. So second, right, the optimizer. How do we want to descend this cost curve? So we looked at stochastic gradient descent already. That's kind of your kind of the standard one that's used all the time. But the more popular one for more complex, higher order data sets is Atom. Essentially, Atom takes a lot of the principles that I already explained to you, but adds a concept of momentum to it. So basically, often you see in these complex kind of optimization planes, the optimizer might get stuck, right? It might get stuck in some kind of local minimum, but we want to reach the global minimum. So this whole like concept of momentum kind of helps it get out of it. Next, the loss function, right? Well, what are we trying to minimize, right? So what are we trying to calculate the error on? Often loss functions for regression, we can use mean squared error, or L1 loss, or absolute error. Or for classification, we often use one called binary cross entropy or categorical cross entropy, which we'll see in just a bit. But that's not really the end to loss functions. Really, loss functions is what are you trying to minimize? So people who work in like the physics informed neural network space, you'll often see them doing cool things with the loss function of saying, oh, like I want you to minimize this thing, but I also want you to like maintain some properties in physics. So they append these or add these things to their loss to be able to do that. Next, epochs. How many passes do we want through the entire data, right? So basically, optimally, right, if you have a data set like this is like a pretty good fit. You're going to have some errors, right? Some greens are on one side and the purples are on the other. But this is pretty optimal for the majority of the data set. This is where you want. This is underfitting. This means you haven't passed your data through the model enough times. So that's not really good, right? So this means the model really hasn't learned the distribution of data yet. Overfitting is if you pass your model or if you pass your data through your model way too many times, instead of like generalizing the model for like, general trends that exist in the data, the model will just kind of memorize the data set. And once it's memorized the data set, the model is kind of garbage, right? Because sure, it works. You'll get really good accuracy on your training data. But when you give new data to it, it's not, you can't really believe if it's true or not. So, knowing when to stop is important. And we'll kind of talk about some of this in a bit. But there is one more like novelty to neural networks, right? So what makes a neural network different from a linear regression model? I'll get back to that in just a second. But if you look at this model, right, really you have some input times some weight matrix, right? But if you take a matrix and multiply by another matrix, the only representations that can be defined by just adding and multiplying things are linear representations. But obviously, just simple linear things isn't going to like make super like unique connections between the data and the output. And so like so this is technically just one giant like regression model without like anything. We have to introduce some kind of non-linearity component to this model in some way, right? So how do we do that? These are called the activation functions. So like a lot of my background was in neuroscience, right? So if activation functions are like, it is a term in neuroscience, and basically your brain, when it's trying to, when a neuron is deciding whether or not to fire, right? It has to meet some kind of threshold to actually decide I'm going to fire. And if it doesn't meet the threshold, that action potential is not going to fire. Similarly, they decided, oh, let's just introduce some activation functions to these neural networks. Basically, instead of just saying, oh, I have this node times all these weight matrices, gets me to the next one. But before passing from this one, again, multiplying by a second set of weight matrices, what we want to do is pass this node, or all these nodes essentially, right, this layer, through some kind of activation function. And we have a ton of them, right? So first one is sigmoid, right? So if you're a super high value, it'll just squish it to 1, super low value, squish it to 0. You have a hyperbolic tangent, leaky ReLU. Really, the most popular ones today are ReLU and leaky ReLU for some cases. So all ReLU does is if the value at this node, right? So this node would be essentially all of these values times all of the weights that connect to this node. If the value of this is less than 0, if it's less than 0, it gets crushed to 0. And if it's greater than 0, it just stays as is. It doesn't change anything. That's what's a max function, max 0x. By doing this, this reel is really popular because doing a simple kind of cutoff like this is computationally very efficient. There's nothing to calculate. You just, if you're greater than 0, you're good. If you're less than 0, you're 0. By introducing this at every single layer, the model essentially learns really, really cool, basically representations through these nonlinear functions that we're passing our linear data through. Yeah, let me know if that didn't make sense. That's like a very important concept. But yeah, so we need to somehow, leverage these nonlinear functions. So let's go ahead and just define some of these for the model we're going to train. So we're going to be training our MNIST data onto their class labels, right? So given the image, we want to predict what the class is. We're going to be doing this first with very simple linear network. So let's say our batch size is 128. That means we're going to pass in 128 samples at a time. Our loss is going to be nn dot cross entropy loss. So this is basically the de facto loss function you want to use for most multi-class classification problems. So this is your categorical cross entropy loss. And what it's empirically doing is comparing the distribution of your output versus the distribution of like the actual data, and then tries to minimize the difference between them. But that's at least what it's trying to quantify, but that's a little bit out of the scope. So yeah, just cross entropy loss is for all classification problems. If you're only doing binary classification, like heads or tails, then you can just use binary cross entropy. You don't have to use cross entropy, but again, they're the same thing, so it doesn't really matter. We're going to use a learning rate of 0.008, and we're going to do 5 epochs. Actually, it takes a while, so I'm just going to do 2 epochs. Yeah, epoch. Well, no, it's fine. Let's just keep it fair. Let's do 5 epochs. I'm going to now, so these are the kind of some of these parameters we need for the model. We now need the data loader, right? So the data set. And so what I'm doing right now are things that are kind of pre-built from PyTorch, because they gave us the data set, right? Normally, if you have a custom data set, you need to write the actual data set class for that one. It's not very hard, but we don't have time to kind of go over that specifically today. But I think we have another HAL training specifically for data sets and data loaders, I think. But either way, yeah, so we're using the data set class that PyTorch already provided for MNIST. But if you had your own image data set or own audio data set or natural language, whatever it may be, you need to write this data set class for it. It's very simple, but again, we just don't have time to cover everything in one go. But once you have a data set, right, what a data set does is it returns one sample at a time. We want to grab 128 random samples at a time from our data set. So how we can do this is our train set will be equal to torch.utils.data.data loader, right? So this is our data loader class. What a data loader needs is it needs the data set class that, again, we call train and PyTorch predefined. It needs the batch size is going to be equal to our batch size. We want to make sure it shuffles the data, right? Shuffling is always really good to make sure everything's kind of nicely mixed together as you're randomly sampling from it. Otherwise, these samples won't be representative of the population you're training from. And then num workers equals 2. There's actually a lot of really cool literature about how to sample properly to kind of optimize deep learning training. But again, we don't have time to cover everything. So that's our train set. And then we have our test set. And so why do we have a train set and test set? So like we said, when we train the model, if we train for too long, it's likely to just memorize our training data. So while we train our model, we're going to train on the training data, but we're going to, in parallel, validate on our testing data. And when we see that the model is doing really well on train and not so good on test, that means we've gone too far, right? You want your training accuracy and your testing accuracy to be about the same or as close as possible. For testing, it doesn't really matter if we shuffle or not, because we're not training or updating any parameters based on it. We're just validating. So now, just as a quick test, right? If we do for image label in train, which again was the data set, if we print the image.shape, right? You can see that a single MNIST image has one channel because it's a black and white image, not RGB, and it has 28 by 28 pixels. That's great. If we do the same thing for the train set, which is our data loader, then we can see we grab 128 images, each image with one channel, again, 20 by 28. So essentially what we've done is grab 128 of these images. So that's how we're going to pass in 128 samples at a time to this model. In our dense model, right? So what is the input? Well, 28 times 28, I think is what, 784. So we're going to have 784 inputs. And we know that MNIST has, what do you call it? 0 through 9. So we're going to have 10 outputs essentially. So let's go ahead and write this up. So, all right, there's one other quick thing, softmax, right? So this softmax equation is super important because again, these node values can technically be anything, right? This could be 10,000, this could be 200, but it doesn't really make sense to just directly use this output, whatever the output, and just pick the output with the high. Now, the output with the highest value will always is the output the highest value, but there's some numerical issues when it comes to comparing this, because you hope, right? You hope that your output should be, let's say we're predicting like numbers 1, 2, 3, and 4. You hope that this first one, let's say if the number was number 1, we hope that the probability, the output should be 100% this one, 0%, 0%, 0%. Now, in reality, it probably won't be that like that. It might be like 70% this one, 10, 5, 5, or something like that, right? It won't ever be perfect. But if we want to compare distributions, you can't really compare 100% to some random number that comes out. So we use the softmax to essentially scale these numbers such that it's kind of like a probability distribution that can then be compared with to what we're actually like using our loss on. And that's where the cross entropy loss comes in. But either way, let's go ahead and quickly write this up. So we're going to do class fcnet. It'll go pretty quick from here. Now that we have a lot of these fundamental ideas down, we're just going to try a bunch of different examples. So we want to initialize our class, right? And this always means self. And we, again, always, like always, we need to initialize our parent class, right? Then we have 4 layers. We're going to basically do 4 layers. So we're going to do self.fc1, fc1, and this is going to be a nn.linear module, and it's going to have 28 times 28 inputs, right? Because we have 784 pixels. So that's 28 times 28 pixels. Essentially, we're going to take every image and just like flatten them into a single vector. So instead of each image being 2D, it'll just be a single vector of values. There are some limitations, and we'll talk about that in just a little bit. But for now, that's what we're going to go with, 28 times 28. And we're going to output the 784 to 64. Now, the important part is we're going to have 4 layers. So FC 2, 3, 4. What we want to do then is the output, the number of nodes we have in the output of the first one becomes the input to the second one. So if we had 64 out, then we have to have 64 in, and we're going to let this go from 64 and just stay at 64. And then if we have 64 out, well, we have to have 64 in, and we're going to output 64 to 64 again. And then we're going to go from 64 again, because we're going from 64, and then we have 10 outputs. How did I come up with all of these numbers? This is just me randomly putting numbers down. MNIST is a pretty easy data set, but when you actually build and deploy these large scale models, the hardest part isn't training the model. It's really just, there we go, sorry. The hardest part isn't really training the model. It's how many nodes, right? How do I know that I should go from 64 to 64 here? There's a massive hyperparameter tuning stage that you need to go to, where you just try a bunch of different combinations of models and, just see what works best. So there's no like empirical way to just like tell, like, this is the way to do it. So either way, again, like always, we need a forward. Our data is X, and we're just going to do X equals X dot view. And I'll explain this in just a second. 28 times 28. So the only issue we have right now is that our linear model expects a batch size, so 128 by 784 input. We have images, right? So our images were, like we saw, 128 by 1 by 28 by 28, or sorry, 124, or I can't remember. Yeah, it was 128. Yeah. So when we printed it out up here, right, we saw that there's 128 samples, and each sample was an image of 1 by 28 by 28. We're just going to grab these images, and dot view is the same as NumPy's dot reshape, and we're just going to reshape these tensors such that we still have 128 batch size, and we're going to flatten the rest as 28 by 28, 28 times 28. So this is just 784. So the output shape of X is now 128 by 784. 128 by 784 can be passed into the model. So then we're going to do X is equal to self dot FC1 X, right? So we're going to pass in our data into the first layer. But after we do that, we want to pass it through a dot reloop. So we're just going to nest the functions here. So this way, we passed our data into the first fully connected layer, and then we've added some kind of nonlinearity to it. You could have done f.sigmoid or leaky relu or whatever you want, but just to keep it simple, we're doing f.relu. And we just have to repeat this a couple of times. So 1, 2, 3, 4. So FC2, FC3, FC4. Now in FC4, the last one, we don't want to apply a relu to it, right? Because the last one is just to map all these learned hidden representations to our output. But we don't want to do relu to the output for any reason, because we want to know which value is greater and less. So if one value is negative, then that does matter. So good. So there's FC4. Now, how do we convert our values? These values here, right? Which could be like 1,000 minus 800. Like it could be anything. There's no control over it. How do we convert it to some kind of probability distribution? Well, what we could do is X equals f dot log soft max self dot xc4. Oh, actually no. So it'll just be log soft max x along, and we want to calculate the softmax not across all the samples, but for each sample. So each sample should be softmax. So the dim should be equal to 1. Now, this is a beginner's mistake, right? Most people I see who are really struggling to train a model, this is the problem they make. You do not need this line. This line should very much be ignored. If you do log softmax and then pass this x into the cross entropy loss, the cross entropy loss expects logits. So basically the raw outputs. And then internally in the cross entropy loss, they will do the log softmax, but they do it with something, they basically do a cool trick, which you learn about if you take more advanced deep learning classes. They do it with a cool trick. So there's numerical stability, right? Because there is some issues with doing log softmax directly. So yeah, this is beginner's mistake. Never do that. Just output, just FC4x, and that's it, right? That's all we need. And then the rest of the stuff will happen inside the loss function without us having to think about it. If we quickly take a look at model equals FC net, right? And then print out the model actually. We can see our model is 4 linear layers. First one's going to take an input of 784, 64, 64, 64, many times all the way till 10, and that is it. So this is our very simple model. Now, how do we do the training loop? Well, our model is equal to, I deleted it. FCnet, right? Our model is equal to that. Our optimizer, just like before, I'm going to just pass through all of this now because it's all the same as before. Model.parameters learning rate is equal to the learning rate, which we defined above just a bit ago, right? So 0.008, we have the loss, we have epoch, everything is up here. And then we have, let's just keep track of how long it takes, is equal to time. And now what we want to do is for epoch in range epochs. Now, if we want to do 5 epochs, this is technically going to print out 0 through 4. So just for visualization purposes, we're going to do 1 to 1 epochs plus 1. For this many epochs, we want to print out the epoch string epoch. Okay, there. Right, so that's the epoch we're currently on, right? And then how do we want to keep track of everything going on? Well, we're going to do losses, right? And so basically losses is as we pass in a little bit of our data at a time, because before we just passed all of it in, but now we need to just kind of find the average loss across all the little batches of data we pass through. So we're going to do for data in train set, x, y is equal to data. Right, so x and y will be our images. This will be of shape 128 by 1 by 28 by 28. And then our y is just, the actual class labels for each one of them. We want to do optimizer.zeroGrad, just like before, right? We always zero out the gradients. Then our forward out will be our model. And we want to put into the model x. And then our loss val, right? What is our loss? Our loss will be that loss function we defined earlier. It'll be between forward, out, and y. Now, once we have our loss, right, we can do losses dot append, loss val dot item. This is just us to keep track of the loss over time, but it doesn't do anything else. Next, we're going to take our loss val dot backward to calculate the gradients. How much do I need to change all these different weights, right? We have a ton of parameters here. We have to update all of them. So we need to calculate the gradients for all of them. And then we can do optimizer.step, right? To take a little step towards the right direction. And that's it. And we just want to print out our NP, let's just do losses, and then NP dot mean losses. Cool. Right, so for every epoch, I just want to print out the average losses across the entire data set. Now, this is going to run, but it's going to take some time. It takes like 3 minutes, right? And so I'm not going to run it. Well, I will run it, but I'm going to run it a little bit differently a little bit later, or in just a few minutes. But basically, up till now, right, we've been running all of our computation on the CPU, right? So if you ran this, it would take about 170 seconds, right? And CPUs aren't very geared towards doing matrix multiplication the ways that GPUs are. And that's why GPUs are so important for a lot of these kind of tasks. So we're going to come back to this in just a little bit. We're going to rerun it, but we're going to do it on the GPU instead. And to run on the GPU, there's only like one or two small changes that need to be made. Basically, the main thing is we need to make sure our model is sitting on the GPU and our data is sitting on the GPU. So if you try to run something and the model sitting on the CPU and the data is sitting on the GPU, it's going to throw an error saying, hey, they're not sitting in the same place, can't compare them, right? So you have to make sure all the tensors, right? So the model parameters and all the data is sitting in the same place. But this is kind of why we do the batching, right? Because if you have a data set that's a terabyte of data, you couldn't just let a terabyte of data be sitting on the GPU at once because there's no way it would fit. So we grab a batch of data at a time, move it to the GPU, and then process it in the model, and then replace it with a new batch of data, and just doing that over and over again. So yeah, there's two CUDA is how we basically move things to anything. So if we can do a quick check, right? Our device will be CUDA if torch.cuda.is available, else CPU, right? So if CUDA is available, then use the device CUDA, otherwise use CPU. If you have a GPU like HAL has many GPUs, you can specify I want GPU 0, GPU 1, right? Whatever you want. By default, it'll just use the first one in the first like PCI slot. So 0, GPU 0, whatever GPU 0 is for you. Another thing for NVIDIA specific, though I don't think you can train on anything but NVIDIA. If you do NVIDIA SMI in the terminal or exclamation to run a terminal command in Jupyter Notebook, it'll print this stuff out where you can see that, hey, so this GPU is a Tesla V100, has 16 gigabytes of RAM. This is my temperature, you know, all the fun stuff all about it. So what we're going to do is just take this data. Again, I didn't run it, but this would have taken about 170 seconds to run here. We're just going to copy it into here. The only changes that we have to make, everything in the loop stays the same. We just need to make sure that our model is on to device, which in this case is just CUDA. And we need to add another line here where, oh crap. Well, okay, good. At least we can show you the error. Right, so it says expected all tensors to be on the same device, but found at least 2 devices, CUDA 0 and CPU. If you see that, that immediately means that, hey, so my model's sitting on the GPU, but it looks like my data is still sitting by default on the CPU. So we just need to go xy is equal to x dot to device, and then y dot to device. Cool. And now this should just work, I hope. Unless I always make a little bug. So let's let that, oh yeah, it's moving. All right, let that go. I'm printing out the loss, right? This is my categorical cross entropy loss. You can see, oh look, in second epoch it went down a little bit. Third epoch it should go down a little bit more, and it'll just keep going down more and more over time. I'm not checking the test. I'm not checking the test loss in parallel, but while that happens, right? Technically, what you should do is just make a second for loop in here for data in test set, right? What you'd want to do is xy equals data should be the same. We want to move the data to this. This goes away, right? Because again, we're not performing any gradient updates when we're working, right? The test data should never affect the model. We're just inferencing on the model. And we want to remove all of this, right? This loss val.backward should go because we don't want to, again, apply any gradients. Optimizer.step should go. What we should add in is with torch.no_grad. Right, so this will make sure that every time we pass data through, we're not building the computation graph again from scratch. This way it'll kind of skip all of that and reduce the computational complexity of actually inferencing on your data. And the last thing you would have to do is model.train, right? So this puts the model in training mode. And then we just grab this, go down here, and we put this in model.eval, right? And so this puts the model in evaluation mode. And the reason you want to do train and eval is because there's some things that we won't be seeing here, but like there's things called dropout layers and things like that, things that we use for curtailing overfitting. By putting in evaluation mode, it turns that stuff off because when you're inferencing, right, you wouldn't have that anyway. So yeah, model.train, model.eval, whatever it may be, right? So regardless, right, nice, low loss here. And I'm not going to type all this out, but just to give you a, right, so yeah, basically this is a loss. If you want to check like the inferenced results, right, we could, I don't know if this is going to directly work, but we can try. Right, so basically what I've done here is I have how many correct initialized to 0, the total number of images initialized at 0, and then we're going to set it to evaluation mode, right? And we're going to do with torch.no_grad, so we're not updating the weights in this model in like any way. We're going to iterate through our test set. This is definitely going to break. So let's do a xy is equal to, I can just grab the line from up here. This one, I think that should work. I think so. Well, we'll find out. Yeah, so we have a 97% accuracy. All we've done is iterate through our data. And then again, every batch we grab has 128 samples. So we're comparing what index, right? So basically our last node has 10 nodes. So which node had the highest one, like nodes 1 through, or nodes representing numbers 0 through 9, what was the actual data, what was the true label? And if they're correct, add 1, otherwise, just add 1. And, we have 97% accuracy. Wonderful. Now, next part is we noticed in the last one, right? We added this view, right? And view essentially in our fully connected network, this just flattened the image. Now, if I gave you just a vector of numbers, you probably wouldn't be able to tell what the number is yourself. So it's not the best way. So this is why we have things called convolutions, right? So convolutions are essentially this. So you have some kind of filter, this box, they're called filters or kernels or whatever you want to call them. And they slide across an image iteratively and do some kind of downsampling techniques on it to essentially make some kind of estimation. And the general technique you see for convolution-based methods is the image size starts as 28 by 28, but it gets very small, right? We're going to downsample this image to 4 by 4 while increasing the number of channels, right? We only had one channel here, but we have a ton of them over here. By doing this, we hope that our model is capturing spatial features inside these last channels that kind of represent what this number 2 would look like. These features are then flattened, passed to a linear network, and then outputted to some kind of linear module. That's basically all that's going on. To visualize it a little bit better, right? This is what a convolution does. So this, you can see it moves 1 pixel at a time. This is called the stride, right? So the stride is how large of a step will it take every time. You can see there's a white border around it. That's called the padding. And that basically, if we didn't have padding, there'd be larger amounts of downsample. There is a direct formula. We'll get there in just a second. But any of you guys that are like in electrical engineering or maybe even computer science might have seen it. Filters aren't really a new concept, right? Filters have been used forever. And here's a quick example of the Sobel filter, right? Sobel filter is just a simple edge detection filter. And on this image, if you apply this X direction or the Y direction edge detectors, you get something like this image. What's novel about the neural network is this is very clearly a X direction filter. This is a Y direction filter. And there's a bunch of derivations where you can just empirically find out. In a neural network, these filter values are randomly initialized and learned through training, right? That's the big development that convolutional neural networks added over anything else we've had so far. So what are the parameters for these convolutional layers? We have the number of input channels, how many output channels, right? So again, right, remember we want to expand the number of channels so we can go from 1 to 16, right? So input channels, output channels, the kernel size, right? So what's the size of the filter itself? How large of a step should it take in every iteration? And how much padding do you want to add around the image? Good. There's also a couple of data augmentation. So I briefly mentioned this, and I'll just briefly mention it again. There are a couple data augmentation things you can do as well. Because when it comes to convolutions, they're very powerful, but they're also prone to overfitting. So in our transforms module, we can see we have a ton of different things, right? So the most popular ones that I use all the time is basically every time you pass in an image, randomly flip them or randomly resize them, randomly crop them, do something random to them so that even if you have a small data set, you can pass in a bunch of different quote unquote, I mean, they're basically variations of the same sample. The way you would do this, we're not going to use this now, but I just wanted to give you a brief idea. Let's say I want a transformation pipeline like this. These train transforms .compose. I want a random horizontal flip, a random vertical flip, and then go ahead and just convert this thing to a tensor. And then when we go to train, instead of doing the transforms equal transforms.compose like we did before, we can just pass in transform is equal to train transforms, right? And this is a pretty common set of things that we can do to randomly mess with the image before we pass it to the model. And by doing so, right, we hope that it can learn different features, right? For example, if we're trying to have it classify dogs versus cats, well, sure, it could classify a dog when it's right side up, but if the dog was upside down, it wouldn't know what to do anymore, because convolutions aren't rotation equivariant, they're just or scale equivariant, really, they're just like translational equivariant. So to fix that, we basically just feed in a bunch of random images of the dog upside down, or however, and hopefully through that it'll kind of learn it. But there's a whole literature on the types of pipelines you can make, but that's kind of out of the scope right now. So, but I just want to give an idea that you can do transforms.compose, stack a bunch of transformations together, and then just set that as your transform, and it'll do that by itself on the dataset class without you having to do anything. Next, right? So how do we handle shapes in convolution? And I'll show you why this is a little problematic in just a few seconds. But first, you can directly calculate the size, right? If I know that I have an image of 28 by 28, like MNIST, and I use a kernel size of 3 with a padding of 1 and a stride of 1, I can calculate the output shape directly, right? But if you change the input shape, then the output shape changes. And there's a bunch of finicky stuff that is a little bit of a mess to work with, but let's just go ahead and try it. So this will be our MNIST CNN. We're going to use a convolutional neural network instead here, and then module. Yeah, I got 30 minutes. Sorry, perfect. And yeah, stop me if you guys have any questions. I know I'm going through it a little bit quickly, but init self. Right, so we're going to initialize. Again, like always, we want to do dot init, right? We want to initialize the nn.module class. Module should actually be uppercase M. Okay, great. Okay, so how do we define a convolution? We're going to do self.conv1. I'm just going to call it the first convolution. This is going to be is equal to nn.conv2d. So there's actually a bunch of different types of convolutions you can do. Conv1d, basically, instead of having to learn a 2D matrix of filters, you'd learn a 1D vector of filters, or basically filter weights. And you'd use, these are very popular in NLP kind of context or time series kind of context. 2D is very popular for image processing, things like that. They even have 3D convolutions, and you'd use a 3D convolution in MRI data where you have voxels or point clouds, anything volumetric really is the way to think about it. But what are the inputs to convolutions? You have one input channel, right? Because the MNIST data has just grayscale, so it's a single channel input, and we want to upscale it up to 10 channels. Or upscaling isn't really the right word, but we want to spread the feature space across 10 channels, and we want the kernel size to be equal to 3. Again, right, how you come up with these numbers is a whole parameter tuning kind of deal. Just to give you an idea, right, our image size initially, right, not an exclamation mark, we need a hashtag there. This was our initial image size, right, 1 by 28 by 28. Once we do this, I believe we're going to, let me do the math. There should be a 10 by 26 by 26. Yeah, 26 by 26. Yeah, because we're going to have 10 channels. It's going to expand out to 10 channels. And having a kernel size of 3, we'll do a slight downsample from 28 down to 26. Then we can do self.conv2, and that'll be equal to, again, conv2d. Now, the output of the previous channel, or previous convolution block at 10 channels, so this has to take an input of 10 channels. Let's output it up to 20 channels, and then do kernel size, again, equals 3. And then this will return something like a 20 output channel by, let's see, 24 by 24. Great. I'm just noting these as this is the image shape after applying the convolution. So again, right, we've slightly downsampled the image, and we've slightly, or we've doubled essentially our number of channels. And if you apply a higher kernel size, this number would be even smaller. You've done a larger aggregation. Next, we're going to do self.fc3. Now we're going to take our data and we're going to flatten it. So nn.linear. What will be the input? So we're going to end up with a batch. Each image will turn into a 20 by 24 by 24. So that would be flattened, would be 20 times 24 times 24, and there will be 64 inputs. Yeah, and we're going to output this out to 64. Similarly, self.fc4 will be nn.linear, and we want to output 64 to 10. This is what, this model I know works because I've trained it. But, again, how you figure out all these numbers is probably the tougher part than it is to train them directly. I will just throw the forward function in here just to keep it very simple, right? So we have self.conv1, f.relu on the output of the convolution for nonlinearity. Again, second set of convolution, relu. Then we're going to do a reshape. We're going to flatten, we're going to keep the number of batches, right? So this will be 128 by 20 by 24 times 24, whatever that multiplies out to. This will then get downsampled down to 64, right? So FC3 will take that to 64, again, apply a relu, and FC4 will take 64 and push it out to, basically push it out to 10. This is great until you have a slight change. What if your image is slightly larger? What if you wanted to try the kernel size? I mean, if I change the kernel size to 5 here, right, then this number is going to now change. And you'd have to recalculate it. And that isn't fun, especially if you're working on something like a ResNet. ResNets can have hundreds of layers, so you don't want to have to recalculate it every time. There are easier ways to recalculate this. In our, if you use like PyTorch, I think Lightning and like some of the sequential models they offer have it, but I just wanted to teach it like bare bones. If you only have PyTorch, what do? So this is a little bit tricky, but the idea is the same. So let me actually just copy the first part already, because this is all the same. Right, so this is all the same as before. Now, our goal is to figure out in this linear layer, right, self.fc3 nn.linear, it needs to take something, right, this question mark to 64. Right, now the problem is I don't know what that something is. So let's just create that something for now, and we'll fill it in later. So self.linear flatten, and let's just call it none, right? We don't know what it is. So self.linear flatten, and this is the variable we want to be able to calculate it. Next, self.fc4 will be nn.linear, and it's going to take that 64 down to 10. Right, nothing too new there. What I like to do is actually write two different functions instead of just a forward function. So we can do def convolutions, self x, and then def forward self x. Right, so all I've done is split my function into two. Now the forward is going to be x equals self.convolutions x, right? So basically, I haven't filled it in yet, but x is going to be passed through a bunch of convolutions, and then x will be equal to x.view. This will be the same as before, right? And we're going to flatten it to -1 by self.linear flatten, right? Because that's the shape that we want it to go to. We just don't know what this value is just yet. But it'll be -1 by self.linear flatten. Then x is equal to f.relu self.fc3 x, right? That'll be the input, and then x is equal to f, or actually we don't need it in the last one, which will be self.fc4 x, right? So there shouldn't be anything too new so far, right? All we've done is we have this linear layer here. We don't know what this is going to be flattened to because we haven't calculated it yet, but whatever it is, that's what the input of the linear layer has to be, and that's what this tensor has to be flattened to to be able to, match the shape. So if this ends up being like 128, then we'll have 100, or let's pick a different number. If this ends up being like 256, then we're going to end up with 128 samples by 256 input features, which then get passed into our next linear network. So let's just quickly put the convolutions together, right? The convolutions will be identical to before as well. So that'll be there, and we return out, right? So I haven't really done anything new here, right? I just kind of split my convolution, the forward function, into convolutions, and then, the rest of them. Now, how do we calculate this linear flatten? So on the first time we initialize the model, linear flatten is none. So if self.linear flatten equals none, right? Then what we want to do is we're going to create a dummy variable, right? We're going to create a dummy variable that essentially is a bunch of zeros that we're going to pass through the model, and we're going to pass these zeros through the convolution so we can then calculate what is the output, shape. So we're going to do our dummy is equal to torch.zeros, right? And torch.zero should have shape 1 by 28 by 28, right? This is the shape that we know our data will be in, right? This could really be anything. It doesn't matter. So we could do 4, right? So we have 4 samples. Each sample is 1 channel by 28 by 28. That we know is MNIST. And then what we want to do is with torch.noGrad. Again, we don't want to calculate any gradients based on this. This is really just a logistical thing for us to simplify this process. We're going to do dummy out is equal to just the convolution, right? That's why we split it into 2 parts. We want to pass in to dummy out our dummy, right? And then let's just print dummy out dot shape. And let's actually just find this model down below. Model equals that. That's fine. This is going to break because there's some issues, but that's fine. Because we're just not done yet. So we can see the output of our model with these convolution sizes is four samples, which made sense, by 20 by 24 by 24. Well, this is the same 20 by 24 by 24 we had before. We've just calculated it dynamically now. So all we want to do is multiply 20, 24, and 24 together. So how do we do that? We can just do grab the shape of it. We can index out the first one, right? Because we don't need the sample size, right? Because 4 needs to go away. We just want to do 20 times everything in front of it. And then we can do np.prod, right? We can do the product of these. And this will be our self.linear flatten equals np.prod. And yeah, now it works properly. And so if we just print out self.linear flatten very quickly, we can see that the output of our convolutions flattened will be 11,520, which is the same as before. Now, let's say I wanted, and this is more important if you're doing a lot of testing, right? It's like, oh, maybe a kernel size of 5 is better. Well, this way it works, right? Nothing broke. It resampled it to the correct size without us having to worry about anything. Because if here you changed it to 5, it will, I don't think it'll break, but when you actually try to pass data through it, it'll say it can't do it because the shapes don't align anymore. So this is a great technique. Take a look at the what do you call it, the GitHub repo, and you can kind of take a closer look at this. But I'm just going to keep going. But that's the general concept here. Convolutions, training wise, it is identical. Nothing new in the training here. So here's that same training script from before, but I've just replaced the model name, right? So let's just quickly, test. Right, so our model is this. We made sure the model's on the device. Our optimizer is those same model.parameters, and we just need to make sure that our X and Y, our labels, are also on that same device, and we can quickly train this. And honestly, the MNIST data set's so easy that you're not going to see we already got 97% accuracy in the last one, so it's not going to be much better. But when you're working with complex data sets with large images, and when I say large images, like 224 by 224, 512 by 512, like very large images. At that point, right, you know, convolutions and stuff are much better, because if right now our input, our first layer has dimension 784, well, if you had 512 by 512, right, that'd be a massive linear layer to pass in. So convolutions are way more efficient in terms of the number of parameters they use to represent the type of data that they do. Either way, right, now that you have a model, well, what do you do with it, right? How do you save a model or load a model? Very simple, right? There's two ways to save a model. The recommended way that PyTorch says is use their state dict. Basically, what it does is takes your model, and we saw model.parameters and model.name parameters just a bit ago. Essentially, it's just going to save your model parameters as a dictionary, and then you can just save torch.save your model.stateDict, and just save it as a dictionary at whatever path you want. And then you can load the model you had, right? So model.dynamic mnist_cnn. And then this model can load the state dict after you reload that dictionary again from PyTorch. Right, that's the recommended way, and the way I would recommend to do it. Sometimes you might not have access to this model definition, right? You just need the entire model altogether. Technically, it's like you could pickle it, but they don't recommend that you actually pickle anything. So you just do it this way: just torch.save the entire model, torch.load the entire model. This takes some more space though, in terms of like storage, and so you know it's really just, if you have the model code, then you can just load the weights. If you don't have the model code, you can just load the entire model to begin with. Yeah, those are your two ways. Oh, that should have been down there. Either way, we're going to do one more example. I know it's been almost 2 hours now, but it's about 20 minutes, so I should be able to do this. So everything we've done up till now, again, were supervised learning, because we were mapping some kind of image to some kind of label. But in a lot of situations, like a lot of research that I do, we don't have labels, right? So what do you do with unlabeled data? And one of the most popular methods to handle this is the autoencoder, right? So the autoencoder concept is very simple, right? This first half here, called the encoder, second half is called a decoder. It has its like very popular hourglass shape. And the idea is that you start with an input and you iteratively downsample the data into something called the bottleneck, this red thing here. And then once you reach the bottleneck, you use some kind of linear network or whatever to just re-upscale it such that your output is equal to the input, right? So that's what you want to match. You want to make sure you can reconstruct the output and input. Now, obviously, if your bottleneck is massive, then all the information kind of just directly flows through, and there's nothing like smart happening here. But if your bottleneck is very small, essentially you're forcing the model to say, hey, look, you have all this stuff here, all this information here. I want you to compress it, but I want you to compress it in a way such that we can deconstruct it or reconstruct it again on the other end, right? So it's kind of this game that it plays. So we're going to build a very, very simple and easy autoencoder so you can see what they look like. I'm just going to copy this code and walk you through it because it's very similar to everything we've done so far. This is just based off of the linear network. So let's just first go through the init, right? So again, like always, you initialize. I am setting my embedded dim. So MNIST again starts at 784, right? 28 times 28 when flattened. I want to crush it down to just 16. So instead of each image being represented by 784 numbers, we want to represent the image with 16 numbers such that we can reconstruct that image back on the other side with just those 16 numbers. So all we're going to do is 28 by 28. We're going to map it to 256. 256 will then map to 128. 128 will then map to 64. And then 64 is going to map to 16. And now that we've encoded our data, the second half is symmetrical and just decodes it. So now we're going to go from 16 to 64, 64, 128, 128, 256, 256, 784, right? So you can see it doesn't have to be that the model is symmetrical, but it's just nice and convenient when it is. If you make like a weaker decoder, then the encoder has to work harder to like basically encode more information into that bottleneck such that the decoder can actually make something out of it. Also, for simplicity, all I've done is, oh, I don't think I copied all of it. Yes, I missed a function, but let's just add that in. There. Yeah, okay. So all I've done, just like the convolution example before, I have my encoder and decoder just written as separate functions, right? So encoder will accept some input X, pass all the data through, return it. Decoder will, again, accept some X, pass all the data through, return it. And so my output, my forward, is going to take the input data, the true data, pass it into the encoder, and return our bottleneck, right? So this would be, once you've encoded it, you've reached the bottleneck layer. And then our decoder is going to take that bottleneck and try to decode it and build the output. And what we're going to return is both the decoder output and the bottleneck. This way we can use the decoder output for training, but generally for these kind of things, once you've trained the encoder and the decoder, you just throw the decoder away because you don't really need it, right? All you really care about is the values in the middle here, right? This is the important part. So we just want to be able to easily grab that. So we're just going to return it in our function as the bottleneck, right? So the output of the encoder is a bottleneck, and we want to make sure the bottleneck is used to is sent to our decoder to generate the reconstruction, and we return both the reconstruction and the bottleneck. There is another way. So if you look in the GitHub, there is a convolution-based autoencoder, right? So this uses convolutions and transpose convolutions, but just look at the example on GitHub. It's a bit out of the scope of what we're trying to do right now. So I'm not going to worry about it too much, but there's other ways. Again, let me just, training code is essentially identical. So let's just copy it and add it, right? And I'll walk you through it. So device CUDA, I want to use this autoencoder with the embedded DIM of 16. And you can play with this, right? So if you change this to like 8, right? How bad does the reconstructions give? If you decrease it to 2, right? And basically, how much can the model do based on what's given? We want to take this, send it to the device like always. Optimizer is the same. And so now that we're basically trying to do reconstruction between the input and the output, it's not really a categorical problem anymore. We're just trying to make sure that the pixel values on one side equal to the pixel values of the output. So we can just minimize the mean squared error loss between the generated pixel values and the input pixel values. That's all. Epochs, we're going to train for 20 epochs. I'm just going to keep track of all the training losses and all the validation losses for across all epochs. And then these are for each epoch, right? Because we have many iterations inside a single epoch. What we're going to do is for data and train set. Again, look, we only need X. There is no Y, so we just ignore it for now. So for X in data, we're going to take our data, reshape it back into that batch size by 784 shape, send it to our device. And then again, like always, we want to zero out the gradient. Our model.forward is going to return both the forward out and the bottleneck, right? So it's going to return what it attempted to reconstruct based on kind of the model and the bottleneck, and the loss will, and we don't really need the bottleneck now. So technically this could be like empty, but for now it's fine. And our loss will be between our reconstructed forward out and the true X values. Then we're going to append to here our training loss, our validation, we're going to append the training loss. Then we're going to do a backward step to calculate the gradients, and then an optimizer.step to take a step towards optimizing. Then in parallel, we want to keep track of how it's doing on the test set. So just like before, we're going to iterate through a test set, grab X, reshape it, send it to the GPU. And now just with torch.nograd, because we, again, don't want to do any gradient updates, we're going to do forward out and bottleneck into, we're going to pass our X into the model. We're going to get our reconstruction, and we're going to get our bottleneck. We're going to calculate the loss, and we're just going to append our loss to there. And then for every single iteration, or for every single epoch, right, because each epoch will have many iterations in it, we just want to go ahead and take the mean training loss and the mean validation loss for every epoch, and then just print them out and append them. So I'll just copy this. There's no point in typing this out. So we're going to print out for every epoch, what's the training loss, what's the validation loss, and we're going to append to here our training and validation loss for you can plot it later if you want to. So let's quickly run that. What did I miss? Oh, I don't think I ran this one. Okay, good. Hopefully it starts running. Shouldn't take too long. Okay, there, it started. So, there's the loss. So while this trains, we're kind of nearing the end. So I guess, does anyone have any questions about things I've done so far? That'd be a great time to ask. Okay, that's good. I hope it's making sense for everyone. Yeah, these tools are like super powerful, and there's a lot of layers to it. And then there's like really wonderful packages that exist out there that are built on top of PyTorch. They can use for like different vision tasks or NLP tasks or whatever. So it's really important to kind of understand the fundamentals here and then kind of go on and try to solve whatever you want to solve, I guess. So while that happens, I'll kind of just explain the next chunk. There's only 2 more easy chunks of code or 3 more easy chunks of code. So what we're going to do is we're going to now iterate through our data, and we want to grab the embeddings, right? Because we actually don't really care about what was reconstructed. We just want to grab that like bottleneck, right? Like what kind of 16 numbers did it use to represent each image, right? Each image of 784 had to somehow represent it with 16. So what did it use? So we're going to iterate through our test data. This is us just getting the data into the correct shape. So basically each image is 1 by 28 by 28, but the model PyTorch always expects a batch size. So if we only have 1 image, it really should be, here, actually it'd be easier if I type it. So each image is 1 by 28 by 28, right? PyTorch expects a batch size, but this is just channels by height and width. So if we have 128 images, then it should be 128 by 1 by 28 by 28. If we have 1 image, like in this one that we're going to do, then it's just 1 by 1 by 28 by 28. So image in test. So this isn't our data loader. This is just a data set. Each image is just 1 by 28 by 28. When we unsqueeze it, it turns into 1 by 1 by 28 by 28. I know it's a little complicated, but once you do it enough, it starts to make sense. We want to send that to the device. We want to reshape it such that it's 1 by 784, just to make sure it's flattened for the linear network. And then with torch.no grad, we're going to pass our image into the model, and then just grab the embeddings, convert the embeddings, send the embedding back to the CPU, and append it to these like lists that we have, and also grab the label, right? So we can plot it. So let's just grab all of those really quickly. And then these last couple chunks of code are very, very simple. So all we're doing with this one here is we're going to convert our embedded samples, right? So let's just comment, let's actually X that out. So if we do embedded samples.shape, right? So we have 10,000 images in our testing data, and each image is represented by some 16 numbers. We don't really know what they are. And now we're curious about like, what are they? So we can use t-SNE. t-SNE is a very popular dimensionality reduction algorithm that lets us basically take a data set of many, many dimensions and compress it down into 2 dimensions. And there's a whole literature about dimensionality reduction as well. But for now, we're just going to let that run. These are warnings because there's some like, I don't know, I guess they're changing some things in t-SNE, but that's fine. Lastly, all we need to do is plot our results, right? So what t-SNE has done is taken our each sample represented with 16 numbers to turn into each sample to be represented with just 2 numbers. Some other techniques that exist are like PCA or some other things, but I think t-SNE is the best in kind of showing the clusters. So that's what we'll do. All we're doing here is just converting our data into a data frame. So this is using pandas. So all of this is just take our t-SNE results, right? So it'll be a 10,000 by 2-dimensional vector. We're going to append our labels to it just so we have it all in one place. And then we end up with something like this, where we have all these labels, and these are the two values, right? Our X and Y to represent this label, right? So we've gone through two sets of dimensionality reduction, one through the autoencoder to go from 784 down to 16, and now tsneed to go from 16 down to 2. You could have also just set the autoencoder to like 2, so it could be visualized. You could do it however you want, but the rest of this is just grab it for every group. It's just to plot it really. And you can see that, look, we have, nice little segmentations of, these are the clusters that represent the different numbers. So that means like the autoencoder did indeed do it. So I had a question about the portability of models. Let's see. Like when you train a model on a device, do you have to retrain it when using that model on another device? No, you don't have to retrain it. So okay, I'll get to that in just a second. So yeah, so that's the end of like the tutorial, right? These are the clusters, I guess, of the different digits. About saving and loading, right? This is super important. Where to go? So there's, again, two ways to do it. If you train a model on one device, you can essentially save the dictionary and you have the weights, right? So all your training is all the weights and biases, right? In the linear model, it's just a single weight, single bias. And these, in the linear regression model, in these like more complex, like fully connected linear model, there might be hundreds of parameters, right? But all you're saving is the weights. So if you wanted to load it in another device, all you need to do is bring this code over, right? Like this here. This code needs to come so you can instantiate the model, plus, the relevant imports like torch. And then all you do is model.load state dict, and then you do torch.load that dictionary. And basically it'll take the model that was, so here the model is just being randomly initialized, right? When I make it. And this line's making sure that I'm filling in, instead of randomly initializing it, filling it in with those pre-trained weights, right? So, and we do this all the time, right? You grab like ImageNet weights or whatever. So, yeah, you don't have to you shouldn't have to retrain, right? So often you'll train it on some HPC and then you'll bring it local and then do some kind of inference tasks with it. Yeah. Is there any other questions? I know it's like a ton of material, so, but yeah, the more you do it, it's a very powerful tool. You can use it for, I do research in like a lot of really cool things. So you can use it for a lot. So, okay, I'm done. I don't really have anything else to say. If you guys have any questions, you can stay after the time, I guess. I don't mind answering them. Get the Zoom. I think it takes a week to get the Zoom video recording. I could be wrong. They do have last year's recording where the only difference is I went over the convolutional autoencoder instead of the other one. Instead of the linear one. I think the convolutional one was a little bit out of the scope. But just to wrap this up, right? Basically, there's a ton of stuff I didn't talk about, right? There's an important step of normalizing data. All optimization techniques love normalized data, right? We didn't really talk about that too much, but there's batch normalization, there's pooling methods, there's dropout regularization. All of these things help with like reducing overfitting. There's the transpose convolutions that I didn't talk about. There's embedding layers. And honestly, right now, there's a ton of big architectures that exist today. The main ones right now are kind of your variational autoencoders, transformers, graph neural networks, the new diffusion models that you've seen like for like Midjourney and a lot of those text to image generation tests. And they're really based on techniques of self-supervised pre-training, like the autoencoder example we just did, and like quantization and some of these other things. So, it's like a massive field with huge literature, but you can do all of it with PyTorch. And I think like 90% of it has been done with PyTorch. So it's not so bad. Okay, cool. Yeah, that's all I have. So I guess if you're still watching, you can either ask questions, log off, whatever you want.
Okay, Priyam. Yeah, thank you very much for this great tutorial. Yeah, so we will be recorded and posted online within the week. So hopefully, early next week it will be already online on our website. And the Jupyter Notebook link also will be embedded into that recording somewhere as well. So you will be able to have access to the notebook as well. Yeah, great. Well, thank you. We really appreciate you taking your time to present this tutorial. This is a great service to our community. hopefully there will be more people able to use our systems. So thank you very much, and until next week.
Perfect. Thank you.